Hi, my name is Esha and I'll be giving a presentation on the multiplication of two 16-bit numbers using the 8085 microprocessor. Let's look at what the outline of the presentation is going to be. First, we'll look at the problem statement and why we need to worry about it in the first place. Then we'll look at understanding how and where the data that we'll be using in the program is stored. Then we'll work on building the algorithm, then the code, and finally we'll verify the result obtained from the code. So our problem statement is to write an assembly language program in 8085 microprocessor to multiply two 16-bit numbers stored in memory. In our example, we'll be multiplying 0403H and 0206H. In case you didn't know, the H here signifies that these two numbers are in the hexadecimal number system. There is no direct instructions for multiplying numbers in 8085 microprocessor. So for any reason, if the multiplication operation has to be performed, a code needs to be written for it. As I've said, the data that we'll be using in the program is already stored in the memory. So a single memory location can store 8 bits of data, and we need to use 16-bit numbers. This means that to store 16-bit numbers, we'll be using two memory locations. The first of our numbers is 0403 and it has been stored at the memory locations 0050 and 0051. The lower byte of the number is stored at the lower address and the higher byte is stored at the higher address. Similarly, the second number 0206 is stored at the memory locations 0053 and 0052. These are the memory locations that I have used, and these same memory locations will be used in the code. In case your data is stored in some other locations, those memory locations they will then need to be used in the code. Let's now work on understanding the algorithm. Right now, the data that we need to use is stored in the memory. The first thing that we'll need to do is to load the data from memory into things that we can work with. In our case, these things are the general purpose registers of the 8085 microprocessor. Same as a memory location, a single register can store 8 bits of data. So to store 16-bit numbers, we'll need to use register pairs. Another thing that we need to consider is storing the result that we'll obtain. So if you think about it, the multiplication of two 16-bit numbers can result in a number that is greater than 16 bits. So just to be on the safe side, we will be using two register pairs to store the result. The lower 2 bytes will be stored in one register pair and the higher 2 bytes will be stored in another. In our case, the lower bytes will be stored in the HL pair and the higher bytes will be stored in the BC pair. So the first step of the algorithm is to load one of the numbers in HL pair. And the second step is to shift the content of the HL pair to another register pair. We will be using SP for this. The reason we need to do this is that HL register pair is the only register pair that can interact directly with memory. This means that we cannot load data from memory to just any register pair. We'll need to use the HL pair for that. So after loading the data in the HL pair, we then need to shift that data into some other register pair so that HL pair will then be freed to be used further. So now after step 2, the first of our numbers will be contained in the SP register pair. The step 3 is to load the second number in HL, and step 4 is again to shift the content of HL to another pair, say DE, and set H and L to 0, 0. It's necessary to set H and L to 0 because as DE and SP are now both occupied with our numbers that we'll be multiplying, we'll need to use HL and BC to store our result. As mentioned before, HL will be containing the lower bytes of the result and BC the higher bytes of the result. Step 5 is to add the content of SP to HL. What we are basically doing here is, since there are no direct instructions for multiplying two numbers, we will be using repetitive addition for calculating the product. What we are doing is we will be repeatedly adding one of the numbers to HL, which has been set to 0 initially, and the number of times that the first number is added is equal to the second number. So by now you may have understood that step 5 will have to be repeated again and again. So let's see how we are going to do that. Step 6 is to check for carry. That is, if there is any carry that has been generated due to the previous addition. If there is carry, we will be incrementing the value of BC. Remember that BC is the register pair that is containing the higher bytes of our final result. Else, that is, if there is no carry, we'll move to the next step. Step 7 is to decrement the value of the DE pair. Remember that DE pair is initially carrying the value of the second number. And what we are doing is repeatedly adding the first number as many times as the second number. So we need to know when to stop. The program will stop when the value of the DE pair goes to 0. And how will we know when the value of the DE pair goes to 0? Let's see further. Step 8 is to move the content of E to A. And the next step 9 is to perform the OR operation on the accumulator A and the register D. The result of this operation will be 0 if both the values of the accumulator, which has been loaded with the value of E, and the value of the register D are 0. This means that the value of this operation will result in 0 if the value of the D pair is 0. In no other case will the result of this operation be 0. So step 10 is that if the result of the above operation is 0, the program will end. That is, the program will end when the value of the D pair is 0. And if the value of the operation is not 0, we'll go back to step 5. That was the addition of the value of SP to HL. And all the further steps will be repeated again. Thus, all the steps from step 5 to step 10 will be repeated as many times as the value of the second number. That is the value that the pair was initialized with. And for each addition of SP to HL, we'll check if there is carry, and if there is a carry, the BC pair will be incremented. And when all of this is done, we will obtain a result in the register pairs BC and HL, with BC containing the higher bytes and HL the lower bytes. So let's move on to understanding the code now. This is the snapshot of the code as written in the GNU simulator. The reason I chose to take a snapshot is so that you can see the different colors that the different types of texts are written in. So let's understand all the commands that we have used. The LHLD command stands for loading the HL pair directly. What this command will do is to load the content of the memory location given here and the memory location one higher than given here into the HL pair. So the L register will be loaded with the data at 0050 memory location, and the H register will be loaded with the data at 0051 memory location. Remember that these are the memory locations where our number 0403, that is our first number, is stored at. The command sphl will move the content of HL into SP register. We'll use LHLD again to load the second number, which is stored at the memory location 0052 and 0053 into the HL pair. The XCHG command will exchange the data of the HL pair and the DE pair. Since the HL pair right now contains the second number, that will move into the DE pair, and since DE was previously 0, HL will be initialized to 0. Repeat here is a label, and we'll see its significance further. DAD is a command that will add the value of the SP pair to the HL pair. Remember the step 5 of the algorithm, that was to add the content of SP to HL. That is what we're doing in line 7 of the program. GNC is a conditional jump command, and skip is the label that signifies where the jump will happen if the condition for the jump is fulfilled. GNC means to jump if not carry. That means a jump will be executed if there is no carry generated from the previous addition operation. This means that if there is no carry generated, the program will jump from line 8 to line 10, where you can see the skip label has been used to signify where the jump has to be executed. Thus, if there is no jump, the command of INXB, which basically increments the value of the register pair BC, will be skipped. And if there is a carry generated, then the command will be executed and the BC pair will be incremented. The DCXD command means to decrease the value of the register pair DE. Remember that the decrement of the value of the register pair DE was necessary for us to know when to stop, when the program needs to stop. The move A, E command will move the content of E register into the accumulator. Though the AORAD command performs the OR operation on the accumulator A and the register pair D. The result of which will be 0 only when A and D are both 0. That is, its result will be 0 only when the value of D pair is 0. The JNZ is again a conditional jump, and the repeat is the label which signifies where the jump has to be executed. You may remember that we saw the repeat label earlier at line 7, and it is signifying that the jump has to be executed at the addition command, that is the addition of SP into HL. GNZ means to jump if the result is not 0. That is, the result of the previous operation, that was OR, is not 0. Thus, the program will jump from line 13 to line 7 each time the operation ORA does not result in 0. That is, each time the DE pair is not 0. The program will be halted only when the DE pair goes to 0, and thus we'll be calculating our final result, that was the product of the two numbers in the HL pair and the BC pair, with HL pair containing the lower bytes and BC pair containing the higher bytes. Now let's run the code in this actual simulator. This is the GNU simulator for 8085, and I'll show you that I have already loaded the numbers that we are using in the memory. See on the right side, this is some of the memory locations that the simulator displays for our use. At 0051 and 0050, 4 and 3 can be seen to be stored, and 0053 and 0052, 2 and 6, that is 02 and 06, can be seen to be stored. These two memory locations together are storing the number 0206, and these two memory locations together are storing the number 0403. And these are the two numbers that we are multiplying in our example. In the center, you can see the same code that we just understood in the PPT. So we will be running this code, and notice that right now all the registers in the flags have been resetted to 0. And to run the code, we'll need to go to the assembler and then we'll press execute. So as we discussed, first notice that the values have been changed. So we can see that SP is containing a number 0403, and D was initialized with the second number that was 0206, but now it has gone to 0. That was the condition for our program halt. And our result was to be calculated in BC and HL. So BC is containing the higher bytes of our result and HL the lower bytes. So our result is 081E12. That is, our final result is 021E12H. Remember, this is the hexadecimal number system. So we can use the decimal hex converter that is given within the simulator to check what this number is in the decimal system, and then you can verify the result by yourself also. So our result is 08, the value of the BC pair first, as it is the higher bytes of our result, and then 1E and 1 2. So let's see what this is in the decimal number system. It is 531986. Let's go back to our presentation now. So this is the result that we obtained from the code, that is 81E1 and 2H. So you can check this by yourself. 0403 is 1027 in decimals and 0206 is 518 in decimals. If we multiply this, we'll get this number, and you might remember this is the number that we saw in the decimal hex converter in the simulator. That is the number that we obtained in the hexadecimal number system, and the number that we obtained by multiplying these two numbers are basically equal. We'll go back to the simulator and see for ourselves. These are the two numbers that we have obtained. So using this code, we can multiply different numbers. We'll just need to load those numbers in the memory, and then using these memory locations or some other memory locations, we can use this code to multiply any two 16-bit numbers. That was all from my side. Thank you so much for listening. I hope you enjoyed. Thank you.